Hello guys, and welcome to another video. Today, I will be telling you exactly how large your PC would need to be to simulate the universe. I made a similar video around 2 years ago, but it wasn't the most accurate. So, in this video, I will be giving a more refined version of the PC specs. First of all, we need to know how the computer will simulate the universe. My idea is that it will treat all particles as separate entities with x, y, and z coordinates, and kinetic and potential energy. The computer would only calculate fundamental particles, and things such as atoms would only exist as a result of the fundamental particles reacting with each other. Additionally, the computer wouldn't have to store electrical charges or magnetic fields, because it would instead simply store electrons. And since elementary particles do not have a temperature, there would be no need to store thermal energy. There are a total of 17 fundamental particles. These include the 6 quark types, electrons, muons, taus, and their 3 neutrino variants, gluons, photons, Z bosons, W bosons, and the Higgs boson. So, let's start by finding out the total number of protons, neutrons, and electrons in the universe. We already know that there are around 10 to the 80th power of atoms in the universe. So, we can calculate that the average mass of any given atom is 2.43432227 m, and the average mass of just the electrons of an atom is 0.000846568656 m. So, we can now calculate that there are 1.20627904784 times 10 to the 80th protons and 1.20794365736 times 10 to the 80th neutrons. And we also know that the number of electrons is the same as the protons. However, protons and neutrons are not fundamental particles. Each proton and neutron is made up of 3 quarks. So, in total, atoms make up 8.4489471634 times 10 to the 80 particles. Next, we should calculate the number of photons. The issue here is that photons, unlike other particles, can actually be created and destroyed. Their existence is more like a form of energy than a form of mass. When the cosmic microwave background was created, the majority of the universe's photons were emitted. The amount of photons emitted from stars are only a tiny fraction of the amount of photons in the cosmic microwave background. It is estimated that for every proton or neutron, there are 1 billion cosmic microwave background photons. So, that would be around 2.4142222706 times 10 to the 89th amount of photons. I will just give 2.5 times 10 to the 90th entity spaces for photons for any emitted by stars or other objects. Because there are around 150 million neutrinos of any type in every cubic meter, the total number of neutrinos is 1.2964376 times 10 to the 88. Like photons, taus and muons can be created and destroyed. They are created during high-energy collisions and have very short lifetimes, with muons having 2.2 microseconds, and taus having 290 femtoseconds. Because I am too dumb to do a real calculation of the total number of muons and taus, I will guess that there are around 2.125375 times 10 to the 76th. Finally, I also am too lazy to calculate the number of Higgs bosons. So I will guess 1.3888889 times 10 to the 63rd. For the W and Z bosons, I will just guess that there are 80 times less of them than the total number of protons and neutrons. So, there are 6.0355556 AT plus 78 total W and Z bosons. And finally, since there are around the same number of gluons as there are quarks, there are 6.33733346 times 10 to the 80th gluons. If we add all the numbers up, there are this many total particles. Next, we must find out how the computer stores these particles. First of all, the computer would store all the particles in its RAM, because it needs to process every particle constantly. So, how many bytes would each particle take up? Well, first of all, each particle would need a set of coordinates. Because the universe could technically expand infinitely, the coordinates could not be confined to a set amount of bytes. There is nothing we can do about this, so let's just give the coordinates 27 bytes. If we used Planck lengths as the unit for the coordinates, this would allow the universe to expand by a factor of 5,859 before the coordinates will overflow. Next, we will store the particle type, and let's just make that 1 byte. Then, we need to store the kinetic and potential energy. Each one of them would go up to the Planck energy, 1.22 times 10 to the 19th, and have 100 decimal places. This would make them each 50 bytes. Finally, each particle would need to have a direction. This would be in 3 values, the pitch, yaw, and roll. Each would take up 100 decimal spaces, or 42 bytes. So, each particle would have a total of 254 bytes. That would mean the universe would take up this many bytes of RAM. Assuming that each RAM stick is 16 gigabytes and is 133.5 by 31.4 by 4.125 millimeters, and they are packed as tightly as possible, a petabyte of RAM would take up 1.133221478 cubic meters. So, our PC would need this many cubic meters, or this many cubic light years, of RAM. Next, we would need a CPU to process the particles. The CPU would have to be able to convert kinetic energy and direction into movement, as well as process the countless types of particle interactions, particle creations, and particle annihilations. But because this video is getting a bit long, I will make a part 2. Also, if this video was annoying to you for some reason, then please tell me suggestions in the comments. See you next time, and bye.